Okay, good morning. So in the last class we are talking about half bridge converter. So let's again see what is the structure of the half bridge converter. This is the supply. Two switches are connected, one on the top and one on the bottom across the supply voltage Vg. This is the supply voltage Vg. These two switches, let's name them Q1 and Q2. These are the names. One is on the top and one is on the bottom. They are across this thing, and there are two capacitors which is put in series across the supply voltage Vg also, and the intermediate point B is the connection intermediate point joining these two capacitors. So that is how B is obtained, and then the link that joins Q1 and Q2. In more specifically, this is the source of Q1 and this is the drain of Q2. They are joined, and that point is called A, and the transformer is put across the between the points A and B. So what is immediately you can see that from the circuit point of view, this Q1 and Q2 can be complementary, but they cannot be on at the same time. That is the first constraint, because if they are on at the same time, what will happen is that the source voltage Vg will be shorted. So first tendency will be that to do Q and Q bar, think that they are complementary. Just when Q is on, at that moment the Q2 must be off. Their signals are complementary signals. That is what the first intention of operation would be. However, there is a slight, there is a significant constraint you are bringing in. If you do Q and Q bar on, think about it, Q and Q bar is they're on, then the voltage across Vg when Q is on would be how much? When Q is on, voltage at point A with respect to this reference, this is the reference point, that will be plus Vg, and the voltage at point B will be plus Vg by 2. So therefore voltage AB will be plus Vg by 2, as you see here. Voltage across AB will be plus Vg by 2. Now if you make the rest of the time Q2 on, rest of the time thinking that the signals are complementary. So when Q is on, Q bar is off. If you do that, I am not suggesting, I will show that this is a problem. That's what I am trying to show. Why not? There is no problem from the circuit point of view, but there is a problem from the transformer volt second balance point of view, because transformer volt second balance is expecting that the time for which Q is on, the same time for which Q bar has to be on. It cannot be different, because when Q is on, voltage across the transformer is plus Vg by 2 when Q on. But when Q is off, the voltage across it is minus Vg by 2. Q off or Q bar on. Okay, Q2 on. Q1 is a Q1 on. Let us say Q2, Q1 off. So let us say Q1 off and Q2 on, but rather I will call it Q2 on. Q1 off is not defining it. Q2 on. So minus Vg by 2. So this way, if we want a volt second balance, we want voltage into time, positive voltage into time must be equal to negative voltage into time. So you see that if they are complementary, then I cannot assure it, right? I cannot assure it in general. I can assure it only if D is equal to 0.2. So D is equal to 0.5. D is equal to 0.5. Only then this thing is assured that the duration for which Q1 is on and the duration for which Q2 is on are equal, and they are doing volt second balance. So what will be the more? Yes. Any question?
Yes, sir. Hello.
Yeah. Hello. Yeah. Tell me.
So like by changing the ratio of the capacitor C1 and C2, we can like get different value of D, right? If you
yeah, you can do that, but we don't make the things complicated. We see that with that simplicity, that C1 is equal to C2, design simplicity, still if we can get the control, if we can have volt second balance, that is the point. As you are saying, if I adjust that point, but then also it will happen at one specific duty ratio. It cannot happen in any other duty ratio. Agreed? Now you agree? Suppose
Yes,
you can make it happen at, instead of 0.5, you can make it happen at 0.25. That is possible. But I want it to happen at any duty ratio. I want it to happen at 0.1, 0.2, 0.3, 0.4, 0.5. I want it to happen at any duty ratio. So what then I must do? What then I must do is that I will not go with constraint like that Q1 and Q1 bar, Q1 and Q2 are complementary. Rather, I will say like this. Just look at the signal. This is the duration Q is on for D. D is a general variable now. It can be 0 to 0.5. It is a general variable now. That duration must be balanced by Q2. That duration must be balanced by Q2 on. This is when Q2 is on. This is when Q1 is on. And their durations I matched it. So transformer is happy. Transformer is seeing plus Vg by 2 when Q1 is on and minus Vg by 2 when Q2 on. And their times are equal. So therefore, transformer is happy as far as its volt second balance is concerned. As far as volt second balance is concerned. Right? Right. But then what we have to do? We have to apply zero voltage across the transformer, zero voltage, right? Then it is possible. That means a situation will be there when both Q1 and Q2 are off. See, it's a subtle difference. We are never making Q1 and Q2 on together, but we are making Q1 and Q2 off together. That is where the controllability is coming. That is where we can use duty ratio as a variable. And we want the converter to operate, and we want the converter to have the flexibility of choosing different duty ratios. Why? Because the output voltage, as I said, may vary because of load reason, because of input voltage change, or whatever reason. Some reason output voltage may tend to vary. And how do we how do we again get the control of the output voltage? We again get back the control by adjustment of the duty ratio. That is what I said. Duty ratio is a control variable. So with that flexibility, we must possess the flexibility to choose our duty ratio. It should not be frozen at certain fixed values, because it may work at a certain fixed value for a certain fixed input voltage. But in power converters, everywhere our objective is to ultimately regulate the output voltage irrespective of the input voltage. That is what our objective is. So duty ratio has to be kept. This must be absolutely clear to you. So one end we have to make the duty ratio as a variable varying between 0 to 0.5 in this case, in this definition of TS, this is varying, it can be varying from 0 to 0.5. However, we must also see that we have another constant. Another constant is volt second balance of the transformer. So volt second balance of the transformer is suggesting that the switch duration for each Q1 is on must be equal to the duration for its Q2 should be on. Is anybody asking a question? Then I may. Is there any question? Is there any question? Okay. So next then constraint. This constraint is bringing out the situation that I must put a zero state. Now this is a very tricky thing. One may say zero state means definitely Q1 and Q2 both must be off. This is when Q1, Q2 both off. Both off. This is when Q2 is on. This is when Q1 is on. This duration Q1 is on. This duration Q2 is on. And this duration both Q1 and Q2 off. Okay. So this duration both Q1 and Q2. How do we achieve that? Apparently, you may say that, sir, I will turn off both Q1 and Q. And is that really so? Actually, this point is somewhat like a floating point. It becomes. Is that this is possible if this is an ideal situation that Q1 and Q2 is floating, so there is no current and this voltage comes here, and then this point potential also become Vg by 2, then the voltage across the transformer is 0. It is possible for a very ideal situation. but sometimes things are not so ideal. So depending upon the resistance or impedance of this voltage may drift because you are not solidly holding it. Solidly holding is holding it by switching. Yes.
So like if both Q1 and Q2 and off, then the node A will be kind of floating.
Floating, yeah. So we would like to not rely on this floatingness of the node, and then I will show you how we make this node also go to 0. I will show you that. That is what we'll show you when we bring in the secondary side of the transformer, and I will show you that secondary side of the transformer voltage will be 0, and that will make the node equal to 0. That will make that node go to that voltage across the transformer will be 0 imposed on the secondary side. When you are making Q1 and Q2 off, the secondary side will do something that the voltage imposed from the secondary side of the transformer will be 0. Therefore, being a coupled side, primary side of the transformer will be 0. So that is what we will show you now, right? And another thing I will show you that it is suggesting that you should have Q1 for DTS, Q2 for DTS, and remaining time you will have 0 voltage. So what I will rather suggest is I will make this 0 state symmetric. So what I will do is rather I will show you quickly so that you get the idea of what I am trying to do. I will get DTS first, then give a 0 state. 0 state, that means I am dividing this 0 state into 2 equal halves. I am giving 0 state, then I am giving negative, and then giving rest of the time 0 state. So I will symmetrically distribute the 0 states. Okay, these 0 states will be our freewheeling states. That means the inductor diode conduction state. So these 2 states I will bring in here. So I will do a rather symmetric distribution of the 0 state. I will not push it into one end. I will just make it appear half and half in both the things. Whatever the 0 state is here, I will distribute it this way. So let us now draw the full circuit of this converter and understand how this objective is achieved. Objectives are volt-second balance of the transformer and having a control over the duty ratio, also imposing 0 voltage across the transformer during the duration when Q1 and Q2 both are off. So these 3 things will show you how it is achieved here. So let me take a better more elaborate circuit schematic where I have done the secondary side. Primary side has been explained well enough. So secondary side, we see that we have a 2 coils that are number of turns N2 N2. This is called center tapping of the coil, and see the references are different. Reference is arrow. This reference is shown with an arrow, and this reference is shown with this another kind of earth or ground notation, so that you understand these 2 are different. There are 2 diodes, D1 and D2, and the buck inductor, buck capacitor, buck load. So let's say how does it work if the switching pulses are like this. Let me draw the switching pulses now. Right. So this is the switching pulse. So what I do is first I divide it into let me do it a little big way. So first let me divide it into 2 equal halves. 2 equal halves I divide. So I now do this.
Excuse me, sir.
Yeah. Tell me.
Hello. So could you please explain the secondary part again? Like why we are using 2 diodes and all?
That I will show you why I am using. I have to do this thing. I said no. I have to make the voltage across the transformer coil 0 when Q1 and Q2 are off. I will show you that. So just wait. I'm explaining. Just first see the construction, and I'm now explaining why I need this. I will tell you. So
okay.
So this is the Q1 on duration, and this is the Q2 on duration, and total period is Ts, right? I will now define it. This is Ts by 2. I will now say, please allow me, actual period from the buck converter, you will realize it. Just let me do this. Actual period from the buck converter point of view is this. Buck converter will see dTs by 2. That means the frequency on the secondary side is becoming double. Right, wait, you may not first realize it, but you will realize it. So I am writing it dTs by 2 because that is what, that D is the D for the buck converter, and all the concentration is on the buck converter or the output voltage. So that's why the D I am defining with respect to, not with respect to Ts, but with respect to Ts by 2, because that is what the frequency is perceived by the inductor guy. Inductor's volt second balance will be perceived, will be happening twice in Ts, 2 times in the period Ts. So the actual frequency that inductor perceives, inductor volt second perceives, is Ts by 2. That's why I am defining D in that form, because in the final form I will relate it with D, right? Output voltage I will relate to the input voltage by D. So here it is dTs, here also it is dTs by 2. These two things are there. Rest of the time both Q1 and Q2 are off. This is how it is operating. Let's see what is happening. Let's not make our mind clear and simply see what is happening. So let's see when Q1 is on. It is clear Q1 is on. What is happening? Q1 is on. What is the equivalent circuit? What is the equivalent circuit? Let me do it little symbolically, little not uncomplicated manner. So I already have understood that this time switch Q1 is on and the voltage is plus minus how much? Vg by 2. This is point A, this is point B, that is the transformer. Now this is secondary side, because my focus mostly is on secondary side now. Primary side I have understood. The switch actually on is Q1 on. This is Q1 on. How it is Vg by 2 I have explained earlier. This is the reference point of the secondary side. There are 2 turns. This is N2, both of them are equal in number of turns. Primary number of turns is N1. So, symbolically this voltage is Vp is equal to Vg by 2. Symbolically this voltage is Vs1 is equal to Vg by 2 into N1, N2 by N1. And the same voltage, look at the dot convention here, dot convention here, dot convention here. So this voltage is also plus minus, that is also Vs2 is same as Vs1 with this convention of plus minus. We'll always use this convention of plus minus. So this is there, Vg by 2 into N2 by N1. So with this what happens, this positive voltage forward biases the diode D1. Okay, forward biases the diode D1 and the inductor sees, and but reverse biases the diode D2. Reverse biases this diode D2 is reverse biased, because with respect to this point potential is negative and they are combined together. They are combined together. So the moment this becomes forward biased, this point potential becomes what? Vg by 2 into N2, because diode is on, diode is conducting, diode will be conducting a current, Vg by 2 by N2 by N1. This is the voltage here. This voltage is appearing here. So the diode reverse bias is how much? This point potential is minus Vg by 2 N2 by N1, and this point potential is plus Vg by 2 into N2 by N1. So this is reverse bias. So this cannot conduct. We can forget this part of the circuit in the first part of the thing when Q1 on. The actual switch that is on is Q1 on. This is the situation I'm talking about, right? So this point potential is this. This is capacitor. This is V0 plus minus V0. This is R. This is like first equivalent circuit of a conventional buck converter. What we do here, conventional buck converter, when the switch is on, whatever is happening here, is the similar thing. Now we see what will be happening in the next instant. Next instant is what? Next instant, if you look at it, what is the next instant? When both Q1 and Q2 are off. Both Q1, Q2 off. That is the next instant. But there is an inductor current already developed in the buck converter. Buck converter, because this current is now flowing through this. We can easily analyze if it is IL, then the current is IL here. Current wise we can analyze easily because diode is conducting IL here. To compensate that current, what will be the current? Load current compensation will be IL N2 by N1. That will be first part of this thing plus the magnetizing current plus IMP will be equal to IP. IMP how to determine we have already learned, but qualitatively let us now think that there is a magnetizing current that is flowing through this coil, and this is the load current reflected into the primary side, that is the primary current. That is what clearly you understand what is happening here, right? Right. Then next instant what is happening? Next instant what will happen is that we have turned both of them off. So immediately we won't dictate what is in the primary side. We will not dictate it. We'll just keep it floating. Think that it is floating. I have no way of first knowing this thing. But what will happen in the secondary side is now important, because the inductor must see its current to continue. The inductor means buck inductor. So what it will do? It would like sorry, the red color. Okay. This inductor would like its current to continue. How will get its current continue? You will see that this current. Let us see the continuity of the current. IL comes here, and these 2 points are shorted. So this divides and breaks, and the current returns. Then it sees that there are 2 paths for the current, and it will take both the path. It has no choice. It will take both the path of the current. It will both one part of the current, maybe IL by 2 in an ideal sense, and IL by 2 in another ideal sense, will go and distribute in these 2 divisions and come here and then short here. So, and then join together. This is IL by 2, this is IL by 2. They join together and again become IL. So the inductor will force it. These 2 diodes are now working like a freewheeling diode, right? We have a freewheeling diode here. These 2 things combined together are working like a freewheeling diode. The currents are getting divided into 2 parts. These 2 parts, yeah? And you see, understood this. This current has no preference, because this primary side is floating. Primary side saying, I don't want to carry any current. Primary side, both Q1 and Q2 are off. So primary side, don't depend upon me. I am not doing anything. I will now relax. This is for my to relax. But the inductor is saying, I need a path. Otherwise, my energy, where will it go? So what it does is it comes here, total current has come, and it says there are 2 exactly identical paths remaining. So exactly identical paths remaining, exactly identical way the current will be dividing. So therefore IL by 2 and IL by 2 it will be divided in an ideal sense. If there is some, you will learn when you do better power electronics, you will know that in reality nobody is really exactly identical. This diode drop may be slightly different than the other diode drop. So there will be slight difference in the current sheet, but the point is that current will flow from in both the paths. Both D1 and D2 will be conducting. There is no doubt. Let us first learn with perfect ideality. In reality, it will be maybe one will be 10% more than the other. One will be 20% more than the other. Some such small variations will be there. But total, in the sum, after summing them up, you will always get that this voltage is, this current is summed up to be again coming back to be as IL. Okay, so this is yeah.
So like in this state, if both the diode conducts, then like if we apply KVL, then the total voltage across the secondary will be 0, right?
Yes. That's what you immediately. That's what the point is. If you do the KVL, you will see that this secondary voltage has to be 0. This point voltage is suppose polarity wise I said VS1. Suppose this is VS1. So with respect to this point is VS1, and with respect to this point is also how much? This point it is minus VS1. So we are getting VS1 is equal to minus VS1. So this is true only if VS1 is equal to 0, right? And that is the thing, because magnitude wise these 2 they are same number of turns. If one of them you call it VS1, let me write it more correctly. Let me say VS1 is equal to Vx. Then Vs2 I will write it as, more correctly I will write it as Vs2 is equal to, Vs2 is plus minus minus Vx, right? This is minus Vx. So therefore Vs1 must be equal to, is equal to Vx, and they are the same potential. They are the same point potential you are finding out, right? So if this is Vx, so that means we are saying, you are as if saying Vx is equal to minus Vx. When can it be true? Only if Vx is equal to 0. So which implies that the voltage across voltage Vs1 is equal to 0, Vs2 is equal to 0, Vs1 is equal to Vs2 anyway, because they are of the same thing. So that is the no, I should not write them on minute. This is Vs1. Let me do it actual correctly. This is Vs1. This polarity convention is, it is Vs2, right? So this point potential, I am doing potential of point, let me call V, let me call this point potential as Vx, right? Let me call this potential as Vx, that is with respect to this. So what is the potential Vx? Vx is equal to Vs1, right? And what is the potential of Vx other way? That is minus Vs2, because this potential is this. This is correct. This is correct. So since Vs1 is equal to Vs2, since Vs1 is equal to Vs2, we are suggesting that Vx is equal to minus Vx. That only this is true, Vx is equal to 0. So therefore we are saying Vs1 is equal to 0, Vs2 is equal to 0, and if Vs1 is equal to 0, Vs2 0, Vab is equal to 0. Vab also is equal to 0. V primary is equal to Vab is equal to 0. So that is what that is how the voltage is imposed on the primary. It is imposed from the secondary side, and it is imposed by whom? Actually, who is the cause? The inductor current continuity. The secondary side inductor current is continuing, and it is we have cleverly done a structure such that we use two diodes for freewheeling, and this two diode freewheeling is imposing the secondary side voltage to be 0. And the secondary side, because since it's a coupled circuit, and primary side is not dictating any voltage, because Q1 and Q2 both are off. Since Q1 and Q2 both are off, Q1 is off, Q1 off, and Q2 off. So primary side voltage has no way of dictating. So therefore, this voltage is 0. Okay, that is fine. Yeah.
So like during this duration, when Q1 and Q2 are both off, what happens to the inductor current? Like what will be the nature of the inductor current during this duration?
You cannot guess it. It will be just like a buck converter thing. Buck converter inductor current is 1. But let me draw the inductor current here. Where is that? Somewhere I will draw it. Where is that? Yeah. I will draw inductor current during on time. It had gone up. And inductor current, this is when Q1, Q2 off. It will go down and reach this level. Exactly same level as this. That's why I said it is a periodic with respect to Ts by 2. It has gone up. How much is the voltage of this slope? Vg into N2 by N1 by whatever the inductor, 1 by L. That is the slope. What is the slope of this one? Minus V0 by L. That is the slope of this one. Okay, I will show that exactly same thing happening. I mean, you can guess it. Exactly same thing is happening when Q2 is on. Let us see how Q2 is on is happening the same thing. Let us see that first. Let us see that. Have I answered you? This how inductor current will be like buck converter inductor current. It will go
yes.
This and return back. We'll show you that next cycle also it will be like this. We'll show you this because it is a rectified voltage it is seeing. Inductors that point, Vx point, if I call it this point, this node as Vx node, this node as Vx node, this node voltage will be rectified. One time it will be rectified by this diode, second time it will be rectified by the T2 diode. First time we have shown that it is rectified by the diode D1, second time we will show that it will be rectified by the diode D2. Let me show it with an equivalent circuit quickly. So, yes, please go ahead.
So in the half bridge topology, we are replacing the Q and Q bar switches with Q1 and Q2, right?
we are replacing Q. What? Again, say it again. I
We are
am naming
replacing Q and Q bar switches with Q1 and Q2, right?
the first Q and Q bar is which one? Which one you are referring to? What is Q
So
and
the
Q
half
bar?
bridge topology,
With
the
respect to which?
switches.
I am naming them as physically as Q1 and Q bar, Q2. I am showing that I cannot name them as Q and Q bar because Q and Q bar. That's what the first part of the lecture I was trying to argue, that if I name them Q and Q bar, then I cannot achieve all the things. I cannot achieve variable duty ratio and still achieve volt-second balance. So I have to have independence in them. I have to create something where both Q and Q bar are off. Q1 and Q2 are off. Otherwise, if one is Q, another is Q bar, then other one is complementary. That means when somebody is off, other one is on. But here it is not perfectly complementary. Here there is a state when both of them are off. They cannot be both of them on because that is circuit-wise not acceptable. But they can have both of them off state. That is what I meant now. In the first part I argued that I am arguing that you cannot make these two switches operate with Q and Q bar structure. If it were there, I would have named them as Q and Q bar because it is then clearly mentioning one switch and other switch is complemented. But full complementariness is not acceptable here. We have to create a state where both Q and Q bar are off, so that we get the control variable. This is the zone we want to create, so that we can afford to vary the duty ratio. Otherwise, duty ratio variation was not possible, and it would have only worked with duty ratio is equal to 0.5, because I have to do volt-second balance, and the level of volt-second balance voltages are either plus Vg/2 and minus Vg/2. We don't have varying voltage levels. So that is what we are compelled to operate in this way. Anyway, I have a little bit to think, you will get it. So that's why I have to name them as Q1 and Q2 and not make their switching signals complementary. You see that this is Q1 on, but that means Q2 is off, but this zone, both of them are off. This zone, both of them are off. So now we are coming to the second thing. Second thing is which one? Second thing is when second equivalent circuit is which one? Page.
Sir.
Yeah. You tell me.
The slope should it not be Vg/2 into N2/N1 minus V0/L?
Oh yeah. I am sorry. Yeah, I am doing too much quickly. Yes. Yeah. Just like Bach-Pohn butter. Yes, thank you. Yes, extremely sorry. I made it wrong. Yeah. So the next one is that what you have done. You remember that this terminal you have pulled to Q2 because Q2 is on, and this terminal is connected to plus Vg/2. So what is this plus minus concept wise? The voltage is given here. This is 0, and no, sorry. I am doing wrong. I am drawing it wrongly. I'll draw it correctly.
Sir?
Yeah.
So like in the previous case, what happens to the IM in the transformer?
Oh, okay. Give me a little time. I will come back to that. I will tell you that. Let me first show the power flow. I will come to magnetizing then subsequently. What happens to transformer? I will show you what happens to transformer. Definitely I have to show you because I have promised that this time the flux will be going from minus to plus, and that is possible. That will be possible. I will show you that. So, but let me complete the this cycle. So this cycle, this terminal is A. Now A has been pulled to ground. That is this, and this terminal is B. This is B, and this is connected to plus Vg/2. This is terminal B. This is terminal B. Our dot conventions do not change. Our polarity conventions do not change. So this voltage is now minus Vg/2. So if it is minus Vg/2, let me do a little quickly. You will understand this is minus plus because this is this way. So this diode will be reverse biased. Diode D1 is reverse biased. Exactly similar reason. And diode this one is forward biased. You see now diode D1, because this voltage actually is minus here. actual voltage is minus. Convention is plus here and minus here, but actual voltage is minus Vg by 2. This is minus Vg. Actual voltage is this. So here it is dot. So this voltage is minus and this voltage. So this diode D2 is forward biased now. D2 is forward biased and it then connects itself to this node. And the moment it is forward biased, this point voltage is positive. This diode is reverse biased. So what is happening this time? This time also the voltage here is Vg by 2 into N2 by N1 is coming here at this voltage. And inductor current is again getting a similar cycle. So it is happening twice. That's why I said inductor cycle. The actual switching frequency here is 2Fs. The switching frequency of the MOSFET is Fs. Q1 switches at Fs frequency. Q2 switches at Fs frequency. But the volt second balance at the inductor is happening at 2S frequency. Because this is happening twice. 2 times this voltage Vg by 2 into N1 is appearing here. So like this. And then this, then I will not explain more. So this is how it is happening. But when then, and again when both of them are off, because that is second time happening in a cycle. You can see that it is the second time we are happening in a cycle. When this is off, again the similar equivalent circuit will be coming. The inductor current will distribute between the two, and the voltage will be appearing across it to be 0. Right? You understand that. So what would be the, if one asks, what would be the diode current waveform? If we want to sketch the diode current waveform, what it will be? What it will be? See, you see diode current waveform. Is it possible to draw it here? Let me try to draw it here itself so that you get the idea. So what will be the diode current waveform? Diode current waveform, first part, it will take this current. I am talking about diode D1, say, let us say. So it will be exactly this current, inductor current, because that is what transformer current as well as the diode current. In the second part, what will happen? This is the inductor current slope, but it has now got divided into 2 parts. So I will sketch it just half. Whatever the level, I will go half. Whatever the level, what level? 1, 2, 3. So I have not done 3. 3 half is this. Yeah. Tell me.
So like that line, shouldn't it be like, I mean, it will be increasing till Q1 is on, right? Or is it something like TS by 4? I mean,
which line? Let maybe which line you are talking about? This is the
so like
diode.
So like the Q1 block is like I mean, what is the time instant till which the current in diode is increasing?
During the time Q1 is on. Maybe my drawing is slightly wrong. That's why you are getting confused. This time Q1 is on up to this, and this is the switch here. This is the inductor current. First sketch the inductor current, and during the sorry. Oh. You are happy now? Am I? The question remains or the question has gone? This is the diode.
Yes, sir. It's clear.
Yeah. Then in the subsequent part, it will scale down to half fellow. It will scale down to half fellow. It will come up as long as Q1 is on. The diode D1 with high current is on. Subsequently, it is conducting. It is conducting in a freewheeling manner, but with half the current, because half the current has gone to D2. This half is now here in D1, half is in D2. Then subsequently, when Q2 is on, this current will be 0. I am drawing ID1. I am drawing ID1, and this is 0. And then subsequently, what will happen? Again, it will have a half a current. It will have half a current. This half the current, half the inductor current. So always try to sketch the inductor current first, because others are a function of the inductor current. So this is the diode current D1. This is the diode current D1. This is when half is because both D1 and D2 are conducting. Here only D1 conducting, only D1 conducting. Here D1 and D2 are conducting. Here D2 is conducting. Here D1 and D2 is conducting. And similar way you can sketch the D2 current waveform. I have drawn the ID1. You can similarly sketch, because D2 current, D2 on means here this portion the diode D2 current will be on, right? And transformers current will be what? Transformers current without magnetizing current consideration, the transformer currents. So transformer current will be like what? Prime during on time. Let me one more time do it. Transformer current. This is half. This is D, and this is another portion of the thing. This is TS by 2, right? So how is the transformer current? First, easy part we will do. What? Transformer current is a scaled version when Q1 is on, Q2 is on. It is nothing but a scaled version. This, right? And look at it. When D2 conducts, the current direction is here like that. So transformer current is how the transformer current will be there? It is going out from this. So transformer current here has to flow from going into the cross, because it has to cancel it. So this is this current. So this is the reverse current. So this current will be negative transformer. This is transformer. IP, I am just saying only due to load. IP for load component. I call IP is equal to IP load plus IP magnetizing. I divide it. Magnetizing that I'm not drawing. I'm just saying the consequence of the current flowing D2. This is where D1 is conducting, this one D2 is conducting. And load currents are MMF balanced. So dot cross balanced. So this is where from the cross the current is leaving. So in this side from the cross end, this is dot end, from the cross end the current has to enter. So the arrow is this way. But the convention of current arrow is this. Convention is this. IP convention arrow is this. IP convention, but this current is reverse. So that's why I am drawing in the negative part. And it is just a chunk of the inductor current drawn negative, right? So this is how the transformer current, we understand it. Transformer voltage is negative, transformer current is negative. So I know what is the power. Very easy. But the voltage is where? Where voltage is somewhere here. Vg by 2, transformer voltage. What is the voltage? This voltage is here. This time voltage is how much? 0. So I can easily find out how much is the power. It will balance with the output power. It must be balancing, right? Only question that I have not yet answered is, how is the magnetizing current? Magnetizing current, first of all, you will see that magnetizing current, unlike earlier case, has the ability to go in both the direction. First, look at the topology itself. Look at the topology itself. Look at the topology, core topology itself. Now, suppose magnetizing current, first I have to see whether current can flow positive and negative in the coil. Yes, it can flow in the positive and negative. Earlier, we didn't give the transformer that opportunity to flow the current in positive and negative direction. We didn't allow. We had allowed that. But here we have allowed that. So magnetizing, so the current can go in this way when this switch is on. Even current can go negative way because the diode can be coming. If the switch is on, current can be bidirectional. So magnetizing current has no limitation in this situation. So magnetizing current will be what? Magnetizing current therefore will be symmetrically distributed. So what it will be? Let me draw and then give you the idea. So magnetizing current I am drawing here. I am drawing the magnetizing current here. Let me draw with this is the magnetizing. This is the zero level. So let me draw. The first part, it must be increasing because voltage is plus Vg by 2. So I will say it will increase because it is having the ability to go negative. It will symmetrically place itself in this manner. It will be starting. This is zero level. This is starting from this something like that minus I P M. So it will go from this to this. Then due to I will draw it a different color. I will tell you why I am drawing with a different color. This time, since the switches are off, primary current will be 0. Primary current will be 0. Magnetizing current cannot remain in the primary. So where will it go? It will go in the secondary. but magnetizing current will remain. And since the voltage is 0, magnetizing current value is not changing. So if I draw magnetizing current this time, I am drawing with a new color. Why? I'm trying to say that this magnetizing current is actually in the secondary. I'm drawing with a new color, this color, because primary doesn't have the magnetizing current now. It is now in the secondary. Similarly, when the subsequent thing comes, so let me do the subsequent thing. This means here, subsequent thing, what will happen? This current, the voltage is minus Vg by 2, minus Vg by 2. So what will happen? The current will be going negative. Slope will be negative. Magnetizing current. Let me do it in red, because I'm doing it red because it is now again come back, jump back to the primary. And what will happen in the next cycle, next period, when both Q1 and Q2 are off? Then what will happen? It will again jump back to the secondary, because secondary side is shorted and the current can flow. I will show you how the current can flow. So, so this is the thing, and the current can flow. So, so where is the color? I use this color. This is the color. So let me write it so that this is in the secondary side, this is in the primary side. And the overall waveform is the pattern of the magnetizing current or flux, synonymous. This is the IM. This is the magnetizing current of the thing. One thing you must be clear, though I have made a slight mistake. At this moment, this will be MMF adjusted. That means that due to jump, it may go lower, because suppose N2 is less than N1, N2 is less than N1. So it will be, how much will be, the N1 I1 has to be balanced by N2 I2, and N2 is less. So what will actual value of magnetizing current will look like is this secondary side current. It will jump. It will jump, because this value, if it is N1 into I1, this value would have to be N2 into I2. So this level will jump. And here also in the secondary side magnetizing current realization, you will see the magnitude has changed. This magnitude has changed because it is flowing in the secondary side. And this is adjusted by, let me write qualitatively, this equation it has to go N2 I2 is equal to N1 I1. With this formula it will go. Okay, and so you hopefully you get a if question is there, please feel free. I'll wait a little bit for the questions. Yeah. Tell me. Yeah.
So when the Q1 is on and Q2 is off, so the magnetizing current behaves like a bipolar, right?
Yes, it builds like a bipolar because it has the ability to go negative and positive. But tell me, will you realize it? Mostly you will not realize it, because the transformer current is summation of the magnetizing current and the reflected load current. And the reflected load current being dominating, you will not much realize it, this negative thing. Because what will be the actual transformer current? Actual transformer current, somewhere you have drawn the load component of the current, you have drawn somewhere. Yeah, yes.
IP plus IPM.
Yes. Where is that? I had drawn a transformer current somewhere.
So above it only.
Above the magnetizing current, I think you.
Yes. So this was of our load component of the current. This was our load component. IPL I had drawn. Now IPM, this negative is slightly negative. You may not realize it. It's much, magnitude is much less. So it will be slightly negative here and slightly positive here. That is what the magnetizing current is. And then due to perfect, because you are doing what is that? Bluntly, very drastically, you have switched to on off. There cannot be any current. The current here cannot be there. Neither load current nor magnetizing current. But it is not a problem for it. It is not a problem for it because it is going to the secondary side. And the secondary side current will be slightly adjusted by the value of the primary magnetizing current, by the value of the magnetizing current. And why the magnetizing current is flat? Because actually transformer, you are not applying any voltage across an inductor, magnetizing inductor. So its current is flat. LdI by dt is equal to 0 because Vg is equal to 0. When the applied voltage across the transformer coil is 0. Whether you look at it from primary or secondary, it is 0. So whatever level it has achieved, it will continue to maintain that. It has to maintain that in that, but it will maintain in the secondary side. So secondary load current, a secondary fueling current. Fueling current is where? Fueling current is here. This is the fueling part of the current in diode D1, in diode D2. Similarly, here some part is in the diode D1 and another part is that. This current will slightly get adjusted, and you see that load current is generally more. So you may not even realize that it is flowing. Your actual current, for all practical purposes, when you do calculations, we calculate it with respect to the load current only. We don't consider magnetizing current in our, unless you are very particular or you have done a transformer design such that the magnetizing current is substantial. When normally we will not do that, because there is no need for magnetizing current to be high. Unnecessarily, why do you increase the copper loss? Because magnetizing current will also produce certain amount of copper loss. So you don't do that. There is no rational reason, right? Only case it may happen that suppose somebody starts arguing, I reduce the load, I reduce the load, I reduce the load further, I reduce the load further. Then some cases it may be comparison come in comparison. Otherwise, we will not even this thing. But we will know what is the flux situation. The flux situation is like this. The current may be this. Flux has flatness. Flux, if I draw, flux will qualitatively be like this. I am doing a different different thing. Flux is like this. A flux is like this. Flux is now maintained by both primary and secondary together. Flux is maintained by both primary and secondary together.
So
Yeah, tell me.
like what exactly does magnetizing current depend on?
Magnetizing current depends upon voltage across the coil and the inductance of the coil and the time.
So like coil in sense, like we're considering transformer, right? I mean for when Q1 is on, the voltage across transformer, it will be VG by 2 VG by 2, right? So
VG by 2.
Why is it like having that slope, like from negative to positive value, it's increasing? Why is that happening?
VG by 2 is positive.
Yes. No.
LP is the transformer inductance of the coil. This transformer, it is a coil, no? Eventually it is a coil, right?
Okay.
So this coil has an inductance, self-inductance you can call it. Self-inductance is normally equal to magnetizing if you ignore leakage. In our case, we are ignoring leakage. So you are ignoring leakage, so this is like this, right?
Yes.
So this is simple. Never forget these sort of basic things. You see what is happening. Ultimately, you are applying a voltage across a coil, right? And this is a magnetizing current. This current is remaining. This current is not compensated by the load current. Other current is compensated by the load current. So that is just cancels each other. This is the true current, true flux, true thing. But its value is small. That's it. It is as much important as anything. Without it, the power transfer would not have happened, because it's a coupling thing. It's what is happening. The transformer is saying, I cannot change this value. Why this MMF balance happens? Because transformer says, I must follow the basic law of V is equal to ND5 by dt. I must follow. And since V is same, whether the transformer is loaded or unloaded, it has to maintain the same effective flux inside the core. And while you are loading it, so loading means what? It's a disturbance to the transformer. It is trying to, the load current when flowing through the coil is trying to change the flux level. So what it understands, oh, I must compensate it, and I must, since it's connected to a voltage source, I will draw extra current to the primary in order to compensate the MMF that is there in the secondary because of the load connection. So that is what is happening. Eventually it will make the net flux as the flux level I am showing. Whether it is no load condition or load condition, it will always maintain this kind of flux level. It is the basics of transformer, right? It will always be. Only thing that you are knowing, that transformer is very versatile. It may understand and give the magnetizing burden to the secondary. In the first year, second year, you have always understood that there was no switch there. There was always understood that it will flow always from the primary. Here that constraint is not there. Sometimes it takes primary as the convenient thing is the secondary side, because the primary side you said I won't allow any current, I have turned off both the switches. So that is where the it uses the things. So you are understanding transformer much better because there are some switches. You are fully exploring all the possibilities that are there in a transformer. Acha, one thing I want to tell you for now, that you may leave for a class. I will continue this lecture for some time because I want to tell you a little bit about the other thing that we will be doing in the experiment, that is flyback converter. I will continue to tell you this lecture so that in case you want to see later and you can see it before you attend the lab class. And then in the next class, if there are any doubts, I will clarify that. Yeah.
So like I had a doubt regarding the current waveform of tapped inductor buck converter. Like if you have time, can you explain that part again?
Not now. I will first do the flyback converter, and I will then if you stay, you stay. Otherwise, one thing you can do, you can write your doubt in a question as a question in and send me an email. I will explain that. I will understand why it happens if I write it in words. You just express your doubt in words. I will just even after that, if it is not clear, then maybe in some way we'll explain in the class. Yeah.
So when the Q1 will be on and Q2 will be off, so the voltage across the inductor in the secondary side will be Vg by 2 into N2 by N1 minus V0, right?
Yes. Yes.
Okay. So the slope will be divided by L, right?
So,
Vg by 2 into N2 by N1.
That is what I have written, no? Divide 1 by L. Why I have done? Divided by L. Sorry.
So it will be divided by 2 also, right? Vg by 2.
Vg by 2. Vg by 2. This is correct. Vg by 2, N2 by N1 minus V0 divided by L.
Yes, sir.
Yes.
Sir?
Yes.
So actually, sir, after that I have a class. So like for clarifying my doubt, should I write you a mail or for that?
You write to my write me a mail. Write to me a mail. I will answer in email.
Okay, sir.
Okay. And if even after that doubt persists, I will again take it up in the class. But first you write me a mail, because I have so much pressure on this thing, that thing, and the lab is creating a lot of pressure on me. There are certain things, subtle things, if you do not understand, you do not understand. But the lab is this 4 hours, so much ideas to convey. I'm struggling, so that's why I'm saying I will continue for some time, maybe half an hour in this, and you may look at the recording, the subsequent part. If you have doubts, send me an email, or in the next class also I will one more time raise the points that I made in the lecture. Okay. Okay, so you may leave if you feel like leaving. You may leave. I'll be teaching now flyback converter. The other, there is a subsequent part to this converter of full pitch converter that I will teach in the class. But since in the lab you will be doing flyback converter, which is very easy converter, which is nothing but a buck boost converter. It is very easy as such. So, but still I have to one time tell you. Otherwise, in the lab class you will say it has not been taught, so we will not do it. This, that, all those things you will say. So I just want to keep the lecture into record, and whoever has time, please look at it. It is very easy actually. Okay, so you may leave as and when you find it convenient. So I am now teaching another interesting converter, that is very isolated converter, that is called flyback converter. Flyback converter is nothing but derived from, not from buck converter, but it is derived from buck boost converter, and it is most optimum in the sense of extra components that we require to convert something. A non-isolated converter to flyback converter, you know that we require some extra components we required. We have seen that for half bridge converter and the forward converter, we have seen that. So non-isolated to isolated, we just to do the transformers volt second balance, we required some extra components. So that requirement is minimum in the case of a extra components were required. Extra components are components minimum requirement. That requirement is minimum for this flyback converter. So that is why it is somewhat popular. It is somewhat popular for low power applications when you don't need anything more than 30-40 watt. This will be the first choice. If you need at least 100 watt, you may have to go to a Buck derived converter topology, some kind of Buck derived converter topology. So let us see the flyback converter. Let us one more time sketch the buck boost converter and see how it easily can be converted into. So this was our switch, and this was our diode. And this was sorry, my mind is differing. Okay, this is our inductor, and we know that the diode has to be like this because current, in order to make it consistent with the current flow in the inductor, the diode has to be put in this manner. Always think what is the direction of the inductor current and choose the diode. R, C, D, Q, VG. R, C, D, Q, VG. These are all our this is the topology, and we had seen the volt second balance one more time. We write when Q is on, it is VG into D plus this is plus minus polarity. We don't change the polarity convention. V naught into 1 minus D is equal to 0. So this is during on time volt second balance. This is during off time volt. What is beautiful about this circuit basic topological configuration is that you get two clear different voltages. One input voltage, one time input voltage only, another time the output voltage only. They are not mixed up during on time or off time. Okay, during on time there is no expression combining VG and V naught. During off time there is no expression combining VG and V naught. So all the time they are separate and segregated. So this separation segregation is prompting you to think, if these two levels are separate and segregated, why can't we make a transformer? Easily, why can't we make a transformer? The transformer is like that. That one time you have connected, you are connecting connecting to one input voltage. You are connecting to this voltage, or you are this side voltage are completely no reference, common reference. Basic point is that there is no common reference, right? This in a transformer, there is no common reference, right? Two coils can be brought in and easily can be brought in, because one time I can say that the VG is with respect to one reference, and another time I can say that V naught is with respect to another reference, and still the volt second balance will hold true. So let us draw that way. Let us draw this inductor into two inductors. We call it split inductors, right? We can easily couple them, not split inductors, coupled inductors. We can easily couple them into two coils. It is basically the same inductor, but we are coupling them. First, let us couple this way itself, conventional coupling itself, right? This is one way, and then this is the diode, and this is the capacitor, and this is the resistor, right? Right. So what way it will work? It will work exactly the same way it was working in as a this thing. This is nothing but a coupled inductor. Same inductor split into two coils. You may even keep 1:1 trans ratio here, or you can adjust. You can have keep. So then, what is the volt second balance of this structure? Okay. So what is the structure? This is the, I will say this is the inductor, same inductor L here and L here. Though it has two coils. Now coil 1 this is the coil 1 and this is the coil 2. The trans ratios are equal. The values are equal. I can keep the values equal as long as the trans ratios are equal. Okay. So both of them I have kept same number of turns, let us say, and that's why the inductance value is the same. Okay. So what is the volt second balance? When the switch is on, the voltage here is plus minus, right? So this is VG. Okay. What is happening? Let us see what is happening in the secondary side. If it is plus minus, this side is plus minus, then the diode is reverse biased, right? So diode is reverse biased at that time when the switch is on. Let me draw the equivalent circuit then to understand it better. Plus minus, this is VG. This is also VG, plus minus VG, right? And this diode cathode is getting positive voltage and the anode is another voltage, V0, which is this voltage you are getting, and therefore this is reverse biased. This diode D is reverse biased. It will remain reverse biased. So there is no current in the secondary side, as like a other buck boost converter. This capacitor is discharging. This current is storing in the inductor. This inductor is L. Okay, so this I can say that IQ is equal to IG is equal to this this current of IL, inductor current. This inductor current, if I call it IL, this current is IL. The first part of the IL is going to this coil, and in the second part, what will happen?
Sir.
Yeah.
Why is D reverse biased?
Why is D reverse biased? Why is it reverse biased? Is this? What is the voltage across this? This one. What is the voltage across this one?
Like, can't V0 be greater than VG?
Achha. Good question. Can it not be greater than VG? Actually, it won't be greater than VG. That will do when we do the full stuff. I will come back to that. When we do that, we will get such a value of V0, which will never be possible to make it reverse biased. It will not be possible to make it reverse biased.
Sir, but is V0 not negative? Like in buck boost, the output voltage is negative.
The output voltage is negative. That's why I am saying. So this voltage is negative and this voltage is positive. So you will never be able to get it reverse biased. In this situation, we have not changed anything. So this voltage V0 is less than 0. So therefore, with respect to this ground, here now two grounds are different. So V0 is 0. So diode is always reverse biased. Okay, we'll never get that. That's what I was saying, that if we do the volt second balance, we'll realize that I am not changing the volt second balance at all in this structure, because this inductor is there. Second inductor is not any way affecting the circuit. No current is flowing through it. So here the same volt second balance is VG into D. And the subsequent portion, when this switch is off, then what happens? This inductor energy, dot to cross energy, will now try to flow in the same way. There, this inductor energy, dot to cross energy, the energy has been stored. It will like to continue. So what will happen in the second case? In the second case, when you have turned off the switch, means primary side is open. Primary side is open. This is open. Primary side L is open. This is coupled. The secondary side L, but primary side dot is here dot. And earlier the current was from dot to cross. Now also current has to flow from dot to cross. That has to be, because this is the flux level current. So it has to flow. So what will do? It will take a path. It will get a path. It will create a path. And this creation of the path will actually physically charge this into plus minus. Though the convention of the polarity is plus minus. That is how we define V0. But actually it's plus minus. So now this diode, if I look at it, this diode is what? Cathode to diode. So voltage polarity wise, this is now conducting. This will be conducting. This current will force it to conduct. There is no red color. Let me do red color. This current will conduct. There is no way that it can avoid conduction. This way, this diode is now conducting. It will be, this current has to be continuous. This current has to be continuous. It will force the diode to conduct. And then when it is conducting, you see this V0 is getting applied. The coil voltage is not initially decided by the primary thing. Primary is floating. In the beginning, you can think like that because Q is off. The switch Q is off. So, but what is happening? The diode is forcing the voltage, and that voltage is V0 here. So, this voltage, convention wise, I will say it is plus minus. Convention, let me write it with this. Convention voltage is plus minus, right? So that voltage, convention voltage V0 is appearing here. So again, the volt second balance, if I write, I will write Vg into D plus this voltage is plus minus. So therefore, this voltage is also plus minus, and turns ratio we have taken as equal. So I will say Vg V0 into 1 minus D is equal to 0. So this is exactly the same equation we have done. We have simply done nothing. Equivalent circuit was nothing. We have simply put two coils in the inductor. That has been possible because this equation is suggesting some decoupling. On state and off state voltage decoupling it is suggesting. So I can use two coils. There is no like that. And immediately I have got an isolation. I have got an isolation in this. And this is not like a true transformer. This is like an inductor, but split inductor. So what will be the primary current? If we want to sketch the primary current, it is like an inductor. Whatever earlier, this is the primary current, IP. What is the primary current? Earlier this. Because in your mind, combined together, they are forming an inductor. The second part is here. Combined together, this is an inductor. The old inductor. I'm just drawing over there. Old inductor, but one part you have given, that's why the current can immediately jump because MMF balance is happening. So this is the conventional old buck boost, or not old buck boost, but this time IP is the blue one. IP current is blue one, and this is red one is the secondary current. IS. Okay, this is what. But what is the polarity convention of IP and IS? So let me define it very clearly. IP is in this way. IP I will define it in this way. This is IP, and IS also I will define this way. This way, red. IS. Because that is the true direction.
Sir, the end of the capacitor which you have marked as positive, that is also grounded. So the other end will be negative. So how the diode is forward biased in this case? I could not understand it.
The actual voltage here is what? Volt second balance. Actual volt second balance is suggesting what? For a common VG, V0 is negative. So that means the true polarity of this thing is minus plus. Okay. However, the inductor forces the diode to, this current must flow. It doesn't now depend on this voltage. Whatever may be the voltage here, still it will, like even a buck converter. How does it then conduct? You will see buck converter, let us say.
Sir. So like in this case,
if there is a current build up here, this is plus and this is minus. You may say that this minus terminal is cathode, so it may be reverse biased. You may say that, but it doesn't matter. Any voltage it may be anything, as long you cannot disrupt this thing. So it will first force the diode and let other people decide whatever the voltage is. It will first see, this will first force a continuity path. This is this only thing it is checking that this arrow and the diode anode is continuous or not, consistent or not. It is not checking this thing. It is not checking at that moment. It forces it. Then when it is shorted, then you decide what is the voltage across the inductor, because that is what is undetermined thing. Capacitor voltage is frozen. It is a capacitor. It stores the voltage. Its voltage level doesn't change. What changes is the inductor voltage. That is variable. Do you understand it? Here you have to understand that. Since it is an inductor, its current will make sure whether at that moment the capacitor voltage polarity is immaterial. It is only has to be consistent with circulation, this current. The anode has to be in the correct direction. The moment it has happened, because inductor, where is the energy going? You are not letting energy, it has to happen path. So what it does, it define, you may say that temporarily it gets such a voltage that effectively diode voltage is zero. This voltage is so, and effectively that is what you are saying, because after conduction, what is the voltage across the inductor? What is the voltage across the inductor? Voltage is equal to the capacitor voltage plus the diode drop. So that much voltage it will drop, develop this inductor coil, and it will clamp it, because it cannot change the capacitor voltage, and this energy has to be continuous, this current has to be continuous, and it sees that the diode is placed consistently is consistently placed, because its anode is in the same direction as the current needs to flow, because earlier current has flown from dot to cross. This current also has to flow from dot to cross to maintain the flux, right? So it will take that path. Hello, anything? Somebody was asking some question. Yeah.
Yes. So like I was asking, like when the switch was off, the current from the primary will jump to the secondary and force the diode to conduct, right?
Yes, yes. When you have to see, first thing you have to see if any energy storage element is getting continuity in its thing or not. In the case of this is a coupled inductor. In the case of this thing, it is taking continuity with two coil currents together. So in one time, one coil current can conduct and have that. Then if you forcibly, the Q turning off is forcibly discontinuing that, then this energy will try to see another path, and it sees that that path exists in the secondary side. Because the diode is, if you place the diode wrongly, diode will blow, just simply because this inductor will try to develop as much voltage as is necessary to kill and to continue the path. So the diode will be eventually ruptured to make sure that the energy gets a path, right? So if you put the diode wrongly, it will develop such kind of high voltage across it, and it will this. But now here it is happening, it needs to develop slightly higher voltage, V0 plus diode drop. That much voltage it needs to develop. The moment it develops that voltage, this is it gets a path and it is happy. It will not do anything extra. It will not do anything. Kirchhoff's law is valid. The loop equation is valid. So that's what we are seeing here. That's what we'll be seeing here. Circuit conditions decide when a diode conducts. Circuit conditions decide when a diode conducts, and circuit conditions decide when a diode turns off. Circuit conditions. Yeah.
So like this converter, in terms of all the other isolated converters that we've studied, like this seems to be simpler, and also in terms of loss, it's better. I think there is no loss here also.
It is definitely simpler, but you must understand that it is isolated, but it is not really like a transformer. It is a coupled inductor, because its flux levels are at this level. Its flux levels at this level, high level. In a transformer, we said that the flux levels, if I draw the flux levels of a transformer, we said either it is like this, or it is maybe like this and like this. It is low and this thing. But here this fellow is like an inductor. It will have, you need to put an air gap, and you have to have that. But the moment you are simpler, definitely you don't need anything extra, right? But you cannot say that it is better. Better, why you cannot say is that, because you see the entire power is coming, is confined to only DTS zone. So for relatively this thing, the level of voltage, level of current could be higher. And output power is also getting distributed to the load in only 1 minus dTs joule. So again, the level of current would be relatively higher. In a buck converter, you get advantage in the output side because the inductor is permanently connected. In the boost converter, you get advantage in the input side. That is what. Here the advantage, it is giving advantage in no side. If the current is not continuous from the load, neither current is continuous from the load, neither is current nor is current continuous to the, neither current is continuous from the source, nor the current is continuous to the load. So that is a limitation, because of which this switch's rating will be much higher. It has to handle for the same power much higher current levels. Average value may be set. Average value is not the only concern. The current levels also some concern, because when you learn about switching losses, the current levels have to be taken into consideration. So it is simpler, but it is mostly used for low power applications. It is not used for high power applications. It is used for some converter up to 50 watt or so. But if you want to construct a 250 watt converter with this, you will struggle, because the device rating will be abnormally this thing. And you know that relatively speaking, if a current is peaky type, then the RMS current increases, right? You know that, right? If you, instead of this, if I can get a same average value through this will have less RMS value than this. You know that. So we normally want to have a better distribution of current. We don't want it to be very peaky. It has increases switching loss. It increases, relatively speaking, RMS current. RMS current is more if the duty ratio is relatively less. That is RMS current. For the same average value, RMS value will be more if the duty ratio is less. So here that situation is coming. In one period, only Q conducting and the energy is coming. That time capacitor is on its own. The output capacitor is on its own. It has to support the load during that period when the main switch is on. But again, the energy is not flowing to the inductor when the switch is off. Is not flowing to the inductor. So inductor is not getting continuous supply of energy from the source. It is getting supply of energy only for the duration dTs, and the load is getting supply support of the inductive energy only during 1 minus dTs. That time it is getting support. Other time it has to simply rely on its capacitor. Other time is on time. When the switch is on, the capacitor is alone and it has to support the load. So this thing is a little bit problematic for high power. High power, this power level increases, it is high power. So let us take one example and numbers to make this point even more clear. But before that, I want to show that the constraint that the output has to be negative is now I can remove it very easily. What? By doing a dot and cross transformer, that coupled inductor dot convention. If I change, so I am doing quickly with a switch. This is a switch. No, let me not draw with a switch. Let me draw with a MOSFET only. So this is the thing, and what I will do is, now look at what I am doing. I am doing this small trick, a small trick. I am putting it here, and that will make my current this dot to cross. So it will go diode like this. I have made it consistent. Look at that. What I did. I want this. I want again dot to cross here. So this must be diode direction. Diode direction will change, and now charging will be plus here, minus here. Now that will be the charge. This is L. And now I can use chance ratio as well. N1. I can use the chance ratio as well. This is the diode D. This is the diode D. This is the capacitor. And now it is truly plus minus. This is V0 R, and this is truly plus minus. How does it work? During on time, the Q is on and the inductor current has gone up. This is an inductor current, primary current. What will be the slope as per our old understanding of the slope? This slope is Vg by Lp. This is primary inductance Lp. Secondary inductance is Ls. Vg by Lp. This time is dTs. This is the slope. This is delta ILP. This is only the delta ILP part. There is also an initial part that depends upon the load. That we will not know until and unless we consider the load. But let us qualitatively learn the draw it. And this is what is in continuous conduction mode. This continuous conduction mode, it will start from 0. After that, there is no current here. After that, primary current is 0. So that time, what is happening? Secondary current is 0. But after, when the switch is off, let us say switch is, this is 1 minus dTs, and this is primary current I have drawn. This is IP. This is IP. Primary current I have drawn. This is IP I have drawn. So it is 0 after that because switch is off. Obviously, there is no way it can flow. So what about the secondary side? Secondary side during that time was 0. After that, what will be there? After that, it will have qualitatively this current flowing. This current is IS. This current I call it IS. So how much will be the current? How much will be? Again, I will apply trans ratio formula. N1 I1 is equal to N2 I2. So I2 will be IP into N1 by N2. That will be the peak value. MMF balance will be happening. So this has come, and then it will flow and fall this way. Fall it this way. So this is what is the secondary current. What is the slope of this secondary current? Secondary current slope is V0. The voltage across this is this by Ls into 1 minus dTs. Right? So whatever the current is there, this is the thing. And how is the output current decided? This current average value will be equal to V0 by R. This current average value, secondary side, looking at this thing, that is equal to diode current as well. This is equal to IS is equal to ID as well. Secondary side current and diode current are equal. IP is equal to IQ as well. So this type of current and diode current average, that is ID, must be V0 by R. So this area will be equal to V0 by R, right? So what is the area of this overall? What is the area? This is the level of this, right? So okay, we'll come to that a little later. So what is the volt second balance equation in this case with N1 and N2 considered? So N1 and N2 considered, volt second balance is Vg into D plus I will always make a convention of this is dot means this is dot. I will make that convention. So what is the voltage now? Voltage now is, because this is dot, dot is here, so convention is plus minus here, plus convention is plus here and minus here. Convention is plus here. Dot terminal is plus and minus. I should not confuse you. So not confuse you. This is dot terminal. Again, look at the dot terminal. This is dot. This is dot. Convention. This point potential is plus minus. The dot terminal is plus minus. So what is the voltage across it? I can see that V0 is equal to how much? This is V0. V0 is so Vs, secondary side voltage, is minus V0. Secondary voltage is minus V0, and this volt second will plus minus V0, and trans ratio, this is N2 is the number of turn of the secondary, N1 is the number of turn of the primary, into 1 minus D must be equal to 0. So this is the new volt second balance equation. Okay, I hope you have understood. I am sticking to one coil, that is the primary coil, to write the volt second balance. On time voltage is Vg and D. Off time, what is the voltage? With this polarity convention, I have understood that this polarity, this voltage, when the diode is conduct, this terminal voltage becomes V0 plus and minus. But actual convention is this. This terminal is plus. So Vs is equal to is equal to minus V naught. So looked at it, secondary side, it will be minus V naught into N1 by N2. In the primary side, it will be reflected as minus V naught into N1 by N2. So you see now that if I do that, so it is happening what? Let me write it. Vg is going to d into V naught into N1 by N2 into 1 minus V is equal to 0. So V naught by Vg is equal to d by N1 by N2 into 1 minus V, or is equal to d into N2 by N1 into 1 minus d. So you see now no negative sign. So that means same polarity with this reference and this reference, their same polarity will be getting, right? And now what is the output current? I naught is equal to V naught by R. That must be equal to ID, right? If that is equal to ID, that is equal to ID. So what shall I say? What other thing I need to find out is what will be the level wise their okay. So what will be the average values of these two currents? Let us try to find out. What is the average value of primary current and what will be the average value of the secondary current, right? So average value of the secondary current is okay. So average value of the secondary current, if and diode current are equal. So what is the level of this current? What is the level? I know it must be what? Can anybody tell? It must be this level. I am just saying that this level. What is this level? What is this level? This must be I naught divided by 1 minus d is this level. I naught divided by 1 minus d, because it is conducting only during this period. So overall average is I naught. So I naught into full time is equal to this current.
Sir, that level you are talking about, is that the average only during 1 minus DTS?
Yes, that is the level. By that level I mean this middle point which is passing through the middle point, that level. So that level I mean that. So that level is how much? So that level must be I naught by 1 minus d. What I am meaning is that the diode current is, actual diode current shape is this, shape is this, shape is this. This area must be equal to, over a period, this area must be equal to I naught into Ts. So by equating, and this is, I call it, what should I call it? I call it, let me call it Ix or the IDX. Let me call it for IDX. So IDX into 1 minus d must be equal to I naught into I naught. So IDX, therefore, this is IDX. IDX is equal to I naught by 1 minus d. That is the average value of the average value is I naught. ID, this is ID, correct. ID average is I naught, that is true. But this is the level of the current. Let us say primary side, what is happening? Primary side, this current is how much? Primary side current we have done. This level, if I call it IPX, right? So what will be the primary current level? It will be simply related to the secondary current level by number of turns. So it will be I naught 1 minus d into N2 by N1. That will be the level of the this primary side current by simply related by N2 by N1. Let's take some numbers and then find out. And delta IL I have already found out, so there is no issue. Even I can find out from, I need not even assume that, I can find out from here, because this level from the delta IL I can find out this point and this point, and then I do the N2 by N1 transformation and I get this 2 and this 2. So if this point is, let us say I1, let me call it I1, and this point is I2, right? So this point is nothing but I2 N2 by N1, and this point is nothing but I1 N2 by N1. That is the way we can completely sketch all the number of times. And I know from our understanding that these two are related, these levels are related by this number of turns. They will be related. First, I know the diode current. I know the diode current slope. I know the diode current completely from the load side. I know it completely. Then, simply by transforming with number of turns, I can sketch the primary side. Approach should be know what is output voltage, know what is output current, know what is diode current. Okay, know what is secondary side current, which is nothing but secondary side current. Take delta IL, tell delta IL in the secondary, completely sketch ID, then with the transformation N2 by N1 transformation to get primary. So that would be your approach of solving a problem. Let us take some problem. Let us say that VG is equal to 24 volt and V0 is equal to let us say 5 volt. Let us say I0 or V0 by R is such that I0 is equal to 5 ampere. This is the requirement, right? And let us say we have used a trans ratio of N1 is to N2 is equal to 2 is to 1. Let us say we have used this trans ratio. So what it would be? So we have seen that we will find out first the duty ratio. What is the duty ratio? So let's write the equation: 24 into D plus means minus 5 volt into 5 volt divided by N2 into N1, which is nothing but 2, into 2. So 5 into 2 into 1 minus D is equal to 0. So what is that we are getting? 24D minus plus 10D is equal to 10D is equal to 10. So D is equal to 10 by 34, right? So 10 by 34 is the D we get, right? Well, let us keep it that way, right? So what is I0? I0 is equal to 5 ampere. I0 is equal to 5 ampere is equal to ID. Okay. Let us say we have given LS secondary side is 15 microhenry and TS is equal to 10 microsecond. Let us say it is given. So what is the slope in the secondary side? What is the level? The level is ID by 1 minus D. That is 1 minus D is equal to 24 and 34. So that is the level of the current. So ID is 5 ampere. 5 into 34 by 24. Right. 1 minus D. I have done 1 minus D. Correct. 5 into D is equal to 5 is also okay. Correct. So 5 into 34. 5 into 34 divided by 24. So level is 7.08 ampere. Right. Now I will find out what is delta IL.
So 7.08 is IDX, right?
IDX. That is equal to IDX. IDX level. I have found out the level. 5 ampere is the average. Level is the middle point of the ripple is 7.08 ampere. So now new page after this. So okay. So what I am doing is that that is equal to IDX is equal to 7.08. I have to find out delta IL. Delta IL voltage across it is V naught. LS is equal to 15 microhenry. I have done. So this is V naught is equal to, already I know it is 5 volts divided by 15 microhenry into time is 1 minus 10 by 24 into 10 microsecond. So how much is it? 5 divided by 15 into 10 into 24 divided by 34. So it is, I am getting 2.353 ampere. So delta IL by 2 will be divided by 2. So it is 1.176 ampere. So let us qualitatively sketch it. This current is this in the this thing. So this current peak will be this level. This middle point is somewhat, middle point is here, 7.08. So the peak is how much? Peak is 7.08 plus 7.08, which is 8.256 ampere, and the bottom part is 7.08 minus 1.76, 7.08 minus 1.176, that is equal to 5.9 ampere. So these are the two peaks I have got. The secondary side, this is 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 equal to ID diode current is equal to secondary current, right? So what is the primary current? Primary current will be scaled here. So primary current, let me take it in a different color. This is the primary current. So this peak will be transformed as 8.256 divided by 2. So that is 8.256 divided by 2. So this is 4.128 ampere. And the other, this thing will be divided by 2 as well. So that is 5.9 divided by 2. So that is 2.95 ampere. That will be its this thing, and the average of this level of this will be this divided by plus 4.128 divided by 2. It is equal to 3.54 ampere. You can cross check the power. Cross check. It should happen that they are equal. Output power 5 into 5 is equal to 25 watt. Input power is how much? Input power is, input voltage was how much? I said 24. How much was that? 24. 24. Is 24 into this current's average. So this current average is 3.54 into D. Into D is 10 by 34. So it is 24 into 3.54 into 10 divided by 34. 24.99 is coming here. So this is the, that means this is correct. What we have solved is correct. Any comment?
Yes, sir. Sir, earlier
yeah.
we said that the net change in inductor current in one cycle should be 0. So that thing is not applicable here.
No, not I didn't say the net changing inductor current should be. I said net changing flux should be 0. That is applicable here as well. The flux is L1, I1 and L2, I2 together. So everything together. Inductor current is not such an important thing when this is coupled inductor. The flux level is changing the same way. The flux is changing the same way. One case the inductor's value is high, another case inductor value is low. So that's why it is adjusting itself. The number ampere is adjusting itself. So that flux wise it is going like this and like this. It's going like this. Current wise it may be adjusting here, 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 here. This is how the flux is adjusted. This is how the flux is there. How much is the flux here? You can easily find out. L1 I1 by N. Li is equal to N5. Li is equal to N5. It's the general law. So what is the flux at this level? It is L into I by N. So let us say when primary current is conducting. Let us consider what is this. So primary inductance LP, I is equal to 3.54. No, not 3.54. The peak value was how much? 4.128. 4.128 by N. N is suppose N1. Okay. And LP is how much? LP is secondary inductance was 15 micro into 4 because trans ratio is 2:1. So it will be into 4, right? Because N2 by N1 is this. This is this primary inductance into 4.128 by N1. And the secondary side, when we have understood it, what we are writing, the peak current is 8.256. Inductance is 15 microhenry by N2. And N2 and N1 relationship is N1 is equal to 2N2. You see these two are matched. 2 cancels. So these two are matched. These two are equal. So flux is equal. Understood what I did? Or I am doing too quickly for you? This is I calculated. This is I calculated flux from secondary current point of view, secondary side point of view. This is the secondary side point. First is primary side point of view. Primary is LP inductor. At that time, current is how much? Current is I calculated now 4.128. That is the peak current. So L into I by N1. That is the flux. L is how much? 15 microhenry is secondary side. So its inductance into 2 square. That is 4 into 4.128 divided by 2N2, right? 2N2 divided by 2 because N1 is equal to 2N2. And the secondary side, what I got? 8.256 into 15 microhenry divided by N2. You see the expressions are equal. 15 microhenry, 15 microhenry, 8.256 is equal to 2 into 4.128. So they are equal. So what I am suggesting is that your flux is unchanged. Currents are adjusting their levels due to switching. Core point is flux should be unchanged. Flux should come back to its whole initial situation, condition. Right. One more slight change I would like to do here is that is how we draw it. Now we have done everything. Now we'll draw it cleanly. We'll put the switch later. First the inductor. And then the switch. The switch I have replaced it because normally it is easy to give a gate drive with respect to a reference. The way if we push the switch up, then the reference has to be the gate drive has to be with respect to the source because gate is given source. This is the source. This is the drain. This is the gate. We have to give to turn on. We have to give gate to source voltage VGS. In this case, you can give it to the with respect to a low this reference voltage. In the other case, you have to float it. You have to float the source and give the reference with respect. So gate drive is complicated because gate drive's reference voltage has to be at a higher level of voltage. Here it is with respect to the same reference point. So we always try to, wherever possible, we always try to pull the source of the MOSFET to the reference point of the supply. Then the gate application of gate to source voltage is convenient. Otherwise, gate drive has to be floating. Here I can generate a gate voltage and not isolate it and give it to this MOSFET a high and low pulses. I can generate a voltage whose level is plus 12 and 0. The voltage level of the gate voltage is plus 12 and 0. I can apply plus 12 volt and 0 volt. And the reference is same. Reference is same for this voltage. But if instead of that, if we had switch here, and inductor here, here also I have to give gate to source voltage of 12 volt to turn on. So where? But this point potential is not connected to this. This point potential is going where? When the switch you turn on, this point potential is Vg. This point potential Vg. Then you have to give this voltage with respect to this reference. This voltage is Vg plus 12 volt, which is difficult, which is, you need an isolated gate drive there. There you need isolated. Here you can use non-isolated. Like the way we do the isolate primary and secondary, then the gate drive part also you have to see whether we need isolation or not. With this type of connection, we prefer this type of connection over that type of connection. Because in the other type of connection, you can see that the moment the switch is on, in order to sustain it to be on, we require a voltage which is higher than the source voltage. But the source voltage itself has gone to Vg after Q1. In this state, source voltage itself has gone to Vg. This is Vg. So itself has gone to Vg means the gate voltage has to be higher than 12 volt, higher than that to keep the switch on. Otherwise, it will turn off. In the beginning, you may argue that there was no current and so it was connected to this and all that. I turned on with this. But the moment you turn on, you see that it will turn off. It will not remain on. So this is a simpler and preferred connection of primary. After that, the secondary connection we have already done. So this will be this will be the flyback converter we will see in plus minus V0. This plus minus V0 is truly plus minus V0. This is real plus with respect to this reference, and this has a different this thing. So you really not required much extra component. You really required only one coupled inductor, 2 coil coupled inductor to isolate this, to produce this isolated topology flyback converter from the core topology of buck-boost topology, buck-boost converter. So this is what is the thing. However, this one very important thing which we have not discussed is that whenever there is a coupled circuit, there is a leakage circuit, leakage inductance, and that leakage inductance creates some sort of problem in the circuit. When you suddenly, this Q is on, and when you suddenly change the transformer primary's leakage inductance is then still wants to this, the part of the inductance that is coupled to the secondary. Suppose this part of the inductor is coupled to the secondary. This is a magnetizing part. This is LMP. But there is also L leakage P, that part. that part is not happy. You can immediately transfer the current that was flowing here and to there. So this is dot. Dot to cross. Suppose it is dot to cross. Dot to cross. So here it will be also dot to cross. You can immediately show it there. That is okay. That transfer you can do. But what about transferring the energy that is there in the leakage? So what about the energy that is there in the leakage? So that creates a voltage. It would not like to produce a continue the current like that. So it will produce a voltage like spike like this, and that may destroy the transformer. That may destroy not the transformer, the switch. The switch may get destroyed because of the voltage spike. Because how much is the voltage across the switch that time? Switch voltage is how much? In a conventional sense, when the switch is off, when the voltage is like this. This point is V0. This point is plus minus V0. So this point voltage is minus V0 into N1 by N2, right? With a polarity convention of this side plus and this side minus. This is plus and this side minus actual voltage. That is the voltage across this. So the total voltage is Vg plus this plus is here, this plus is here, this minus is coming here. So this voltage is minus V0 into this, or in this convention this, okay. So with this plus minus convention it is this. So total voltage across this MOSFET is how much? Vg plus V0 into N1 by N2. That should be the normal blocking voltage when the transistor is off. Don't say that when the transistor is off, it is not conducting, so voltage across it is 0. You have to do the Kirchhoff's law. You have to see what is the voltage across it from the Kirchhoff's law. So you have to consider the polarity here. The actual polarity of voltage is this is plus and this is minus, because diode is conducting. If this is plus, then this voltage comes here plus, and this minus comes here this. What is the magnitude? V0. So V0 into N1 by N2 is in the primary side. So as per the polarity convention, minus plus minus plus. So this voltage is therefore V device VQ during off time, during off is this much voltage. So this will be appearing across this, and the along with that, if there is a leakage inductance, some voltage will be spiked, and that voltage, if it is too much, if the leakage value is too much, this may be killed or destroyed. So normally all the converters are actual practical converters come with a clamped circuit. So they all come with a clamped circuit. Practical converters come with a clamped circuit. That means they will be looking like and that causes some loss as well. So clamped circuit means I will take only during off time of the switch. That's why the diode is there. Otherwise all the time was there. And take all the leakage energy and put in a capacitor. All the leakage energy I have not drawn separately. This part has two parts. One is magnetizing and another is leakage. Magnetizing part goes and gets coupled to the secondary side. There is magnetizing part which goes and comes. But the leakage part is, let us say, is a green color part. Okay, but you will not, as such, it is combined together is a coil. You cannot see that, but it is there. So this part of the energy will go there, but the leakage part of the energy will go diode and capacitor. So if this capacitor will charge in this manner. But I cannot keep on charging a capacitor. I cannot keep on dumping. It will continue to end this. So it has to be also balanced. So what, in order to balance it, we have to put a resistor. So I said resistor is not a good component, but in order to make the circuit work, we have to put the resistor. Otherwise, there has to be an extra circuit which is complicating the circuit, which extracts the capacitor energy and puts it back to the source itself. That is called regenerative clamp. That kind of clamp will be called regenerative clamp. When the energy of the capacitor is put in the put back into the source itself with pioneer power electronics converter. But here we are, for simplicity, we are dissipating in this thing, hoping that leakage inductance is not so so big, and the energy involved in the leakage inductance is not so large, so therefore it can be afford to dissipate in a resistor, and it will not significantly affect the efficiency of the converter, and this is that therefore called is dissipative clamp. Dissipative clamp. This design and other things is not in the syllabus, it will be in the advanced syllabus, but you must be aware of the problem. You must not get surprised if you see no flyback converter will come simply like a coil, a primary coil and a switch in the primary. It will also have some kind of diode, capacitor, regenerative or non-regenerative clamp or the dissipative clamp. It will come with the clamp circuit, voltage clamp. We will call it voltage clamp. Okay, so
Sir, can you just explain again what this clamp is doing?
Clamp is doing this. No, this is the coil. One part of the coil is magnetizing part of the coil. So that you have clamp, that you have energy of this magnetizing coil current. You have transferred it here, right? You have transferred it there when you turned off the switch. But what about this current? This is in the leakage inductance. That current needs to be going somewhere, right? Otherwise, that is a problem. So what you do is you divert that current to a clamp, to a capacitor, so that the energy from here goes to the capacitor. Otherwise, the voltage spike here would have been very, very large because there is no defining thing. And as I said, inductor doesn't like that its energy, inductor doesn't like its energy to be discontinuous. So it would have taken a path, and the only path would have been the switch. Only path would have been available is the switch. So it would have taken the path through the switch, and that means a huge voltage would have appeared across the switch. This is the plus terminal. It would have voltage would have appeared, and it might have failed also because that voltage might have been more than the rating of the device. So in order to make it a defined thing, what we do is we put the energy back to the through a diode to the capacitor. Then it has to be dissipated in the resistor. Then what is the voltage in the across the switch? Now we can easily find out. The voltage across the switch is Vg plus V clamp. So this voltage is now appearing as to be Vg plus V clamp. So that we have to design. V clamp we have to keep it limited within the device rating. Vg plus V clamp. Am I answered you or not?
Yes, sir.
This is leakage fellow. So leakage energy, I am putting it into a capacitor clamp. Capacitor clamp means this capacitor, as you know, if I put it that is stable, another kind of stable voltage that is not changing, right? So the voltage across the switch when it is off, how much it is happening? Using Kirchhoff's law, minus plus is Vg, then another minus plus. So together this voltage is Vg plus V clamp. This voltage we are calling V clamp. This capacitor voltage is we are calling V clamp. So the voltage across the device is now limited. It is not unlimited because we can design the clamp voltage to be, let us say, for a 24 volt, we design the clamp voltage to be, let us say, 30 volt. Then we know that the device voltage is never more than 20 plus 30 is equal to 54 volt. That is what we know.
Okay. So, like, had the clamping circuit not been there due to the current discontinuity in the leakage inductor, the voltage across the switch would have been like very high.
Very high. It would have been 70, 80, 110. I don't know. Suppose I have used a 100 volt switch, which seems to be reasonable for a 24 volt application, which seems to be reasonable. But the voltage spike could have been, I have no way of knowing. It is an uncontrolled thing. It depends upon how good one has winding, how much percentage is the leakage inductance. So there is a finite definite possibility, and it definitely will go to a level which is crossing the 100 volt level. So the device will fail. So now we cannot afford this uncontrolled thing. So we are again clamping. So again clamping means we are putting a capacitor. This leakage energy we are putting. Don't misunderstand. Main energy is going to the secondary side, but only the leakage energy will be in the primary side, going to the clamp. So the primary side clamp will be absorbing the energy half IP square. That energy will be absorbing, but this cannot continue to advance indefinitely. So what we have to do is we have to do a balance here as well, as well. So that we are balancing with using a resistor. So ultimately it will come to a steady state, and that steady state voltage is called V clamp. Ultimately it will come to a steady state. Energy coming in through this and the energy going out, dissipating to the resistor. These two operation will come to a steady state, and it will develop a finite, stable, under steady state a voltage without much ripple. Little ripple may be there, but doesn't matter. As we know, all cases there will be a little ripple, but doesn't matter. So that ripple, that stable voltage is the clamp voltage under steady state. Not initially. Initially, every time you do clamp voltage, you will build up, build up, build up, build up. At certain point of time, it will be balancing with the power that is dissipated through the resistance. So that voltage we call V clamp, and then we know that it is not uncontrolled. It is not Vg. It is not Vg plus N1 by N2 into V0, which is nothing but N1 by N2 is 2 into 5, that means 10. So it should have been 24 plus 10 is equal to 34 volt. In an ideal sense, ideal converter, it should have been 35 volt. In a completely badly designed converter, it could be anything and fail. But in a well-designed converter, it would be that, let us say, clamp voltage we have developed to be about 30 volt. 30 volt we have developed. Then it will be 24 plus 30 is equal to 54 volt. But that is within the rating of the device, which may be considered to be a 100 volt device. So that is the way this leakage inductance is handled in a flyback converter, which is always there. One cannot avoid it. Okay. So I think I will stop here.